Hello, and welcome to Astronomy 100. In this video, we're going to begin a section of astronomy that deals with a topic called orbital mechanics. And in this particular series of videos, we're going to describe one of the most important ideas when it comes to understanding our universe, and that is what it means for an object to orbit around another body. And there are many, many instances in astronomy when it has to do with the mechanics of one object orbiting around another one. And so the fundamental details that are part of this topic are going to be related to many other things that we will talk about throughout this semester. So let's go ahead and get started. Now again, the overarching concept is called orbital mechanics, the mechanics of orbiting bodies. And our mission in this series of videos is to understand what it means for one object to orbit around another body. To give you a couple of examples here, the International Space Station continuously orbiting around the Earth is an example of a very large object that is man-made or human-made that is orbiting around the Earth. But believe it or not, the same physics that describes how the International Space Station orbits the Earth is the physics that also describes how the Moon orbits around the Earth as well. So when we talk about orbiting bodies, it's really no different if it's a natural body orbiting around another body or a man-made object. The physics is exactly the same. Now the problem is that there is no way to give a very quick answer to what it means for an object to orbit another body. It requires really a buildup of certain concepts or very, very basic laws of physics that are all tied together to describe this entire concept. So it'll take us a few videos to build up these concepts to be able to, at the end, tie it all together. Now, of course, orbital mechanics is related to the work done by Isaac Newton. Isaac Newton was, and probably is, of course, still today, the most famous physicist of the modern human world, let's say. In the ancient world, there were some very famous scientists as well. But even though Newton has been dead for centuries, he still is the most recognizable scientist and most quoted scientist of our modern times. He was born in 1642, and he died in 1727. Interestingly enough, he was born roughly the same year that Galileo died, so it gives you a little bit of context. He was an English scientist, English physicist, and he is, of course, revered as one of their more famous English citizens, and he is buried in Westminster Abbey, which is one of the most prestigious places that you could be buried in the country of England. Very, very famous individual. Now, he had a tremendous body of work, which is really what we call physics today, and we will only focus on one area of his work, and that has to do with the concept of orbital mechanics. And to understand orbital mechanics, what it means for one object to orbit another body, we have to first talk about Newton's three laws of motion. Newton was able to discover and work through three basic concepts that described all components of moving bodies in a classical sense. And we're going to go through these laws one at a time, and there will be some definitions that go with these as well. So it's a very busy section of the semester. But let me start with a picture here. This is a photograph of a guy throwing a baseball. And the idea of orbiting bodies really goes all the way back to the time of the ancient Greeks. The ancient Greeks had a misunderstanding about what it means for an object to move through space, move through the air, move on the ground, etc. Their concept of moving bodies was one where they believed that all bodies that move are actually trying to come to a rest, so that it was very natural for an object to be at rest, and if you made the object move, the object would then work to come back to being at rest. In other words, you have disturbed it, and so it is naturally trying to stop moving and come back to a rest. Now, it sure seems that way. When this guy throws this baseball, of course, it's going to fly through the air, it's going to arch over, it's going to land on the ground, it'll roll, and it ultimately stops. If you kick a soccer ball, it rolls for a while, but it ultimately ultimately stops. Even if you shoot a very high-powered bullet out of a gun, it'll go a great distance, but it'll ultimately come back down to the ground and stop. So it does seem as if objects that are forced to move will always try to stop. Newton, however, says that we're actually being fooled by outside forces that are acting on the moving body, and that these outside forces are causing us to see a sort of an illusion created by these outside forces. And so he breaks it down into three basic laws, again, Newton's three laws of motion. So let's start with the first one. Now, Newton's first law is one that has two parts to it, and we're going to start with the first part. Here it is. A body at rest remains at rest unless it is acted upon by an outside force. Now, what this law is simply saying is that if something is already sitting still, something is at rest, that it's going to stay that way. And if it's going to move, you have to make it move. So an object that is already at rest is going to simply stay that way. An example that I have here on the screen is if you were to come into a playground and see a swing set and nobody is in the playground and these swings haven't been used for a while, they're going to just hang there and they're going to be stationary. They're going to sit still. Now, if they are to move, you have to make them move. You're actually very familiar with this, even though you may not know it. An example is if you were to walk through a playground, and if these swings were going back and forth, but yet nobody was here, you would be very suspicious. Something is not right, because you know that for these swings to swing, that something has to be making them do that. So we're used to this concept, even though you may not have seen it written out, such as what you see on the screen. Here's another example. If you have been playing basketball in this gymnasium, and if you put the basketball at the center court and you leave the building, and let's say you're the person with the keys, you lock it up, nobody else has access to it, and then you come back the next day, you expect the basketball to be right where you left it. If for some reason the basketball is in the corner of the room or is missing, you would be suspicious because you know that the ball is an object at rest and it's going to stay that way. For it to move, something has to move it. So it's a very basic idea. But the second part of Newton's first law is the part that was related to what the ancient Greeks had misunderstood. Now here's the rest of Newton's first law. He says, however, a body in motion remains in motion, moving at a straight line, in a straight line at a constant speed, unless acted upon by an outside force. Now, I have purposely underlined this portion because this is the portion that many people mistakenly leave out, and it is the most critical part of Newton's first law. What this second part is saying is that if an object is already moving, it does not try to stop. What it does instead is an object that is already moving will continue to move in a straight line at the speed that it is already moving. So in other words, if you were to throw the baseball, what is actually going to happen is if we could get rid of outside forces, the baseball would leave his hand and it would go not like this and curve over, but it would actually continue to go in a straight line at the speed that it leaves his hand. The reason why it arcs over and comes down is the outside force of gravity. So gravity is an outside force that makes it not travel in a straight line. And then of course the fact that it slows down when it hits the ground and rolls to a stop is the force of friction. So friction and gravity are two of the outside forces that are influencing the path of the baseball. What Newton is saying is take away these outside forces and you would actually start to see that this rule is actually true. So let's concentrate on the idea of friction, the forces involved when something rubs or rolls or pushes through something else. And let's start with this idea here. If you're going down the freeway, and let's say you're up to normal traveling freeway speeds, of course what you notice is that when you take your foot off of the accelerator pedal, your car does not immediately come to a stop. When you take your foot off the gas pedal, the car continues to move as if it's trying to stay moving. It, of course, is going to slow down gradually because of the air resistance pushing through the air, the friction of rolling on the road. So air resistance and friction are outside forces. If we could take away air resistance and take away friction, you would actually start to see your car move in a straight line at a constant speed. So your car, by continually coasting after you take your foot off of the gas is your car demonstrating Newton's first law. Let's try to take away some of these outside forces. We're going to move to hockey, and the reason why is because this is now a puck that is moving on ice. And when the hockey players hit the puck, what you'll notice is the puck seems to go very easily, very fast in one direction until it hits the wall or hits another stick, and then it changes direction. So if you were to follow the puck during the game, it would seem as if it is moving in a straight line every time, and it continues to move at the speed that it was hit unless something interacts with it. So the puck is starting to show more of the behavior of Newton's first law, and the reason is because it's on ice. Ice still has friction, but it is much lower friction compared to your wheels of your car on the rough asphalt. So the puck is starting to show more of the behavior by, of course, getting rid of some of the friction. Let's get rid of more of the friction. This is air hockey, and if you've ever played the game, you'll notice that there's air that blows through the holes in the table. And whenever you hit the air hockey puck, what you'll notice is just barely tapping the puck, it seems to move as if it's just being compelled to move. Now, the reason why it's doing that is because the air is making the puck rise above the table, and so there is no physical contact between the puck and the table, and so by riding on a cushion of air, you've greatly reduced friction. And then when you tap it, it starts to move in a straight line at a constant speed because you have taken away one of the outside forces, in this case, the force of friction. Now, to make this go to the ultimate extreme, we would have to go to space. But unfortunately, there are things related to traveling through space that we have to first correct. There are some Hollywood misconceptions that have to do with space travel. And humor me here for a minute because I may be dashing some of your most favorite movies when it comes to true physics here. Now, this first picture on the top is demonstrating one of the problems that Hollywood tends to do when it comes to moving through space. Whenever a spaceship is moving, they always portray the engines continuously running. The problem is that because of Newton's first law, you don't have to do that. Remember that a body in motion continues in motion in a straight line at a constant speed. So if you make the vehicle go to the speed that you want it to do, based on the engines running, once you are at that speed, you turn off the engines and the spacecraft will continue at that speed. There is no need to continually run the engines. Besides, if you did, you would run out of fuel very quickly. So in space, real spacecraft do not have to have their engines run continuously. Now, although Star Wars is one of my favorite series of movies, don't mean to step on anybody's toes here, the one problem with the X-Wing fighter is the wings. In space, there are no need for wings because wings are used when you travel through a medium like air or water. It is the flow of air over the wings that allow you to have the wings make the plane turn, or in this case, the spacecraft turn. So a spacecraft with wings is completely useless because there is no air in space. So spacecraft in reality are not aerodynamic because aerodynamics is meaningless. Let me show you a real spacecraft. This is an illustration of the Voyager spacecraft. There were two of them that were built. They were launched in 1977. And notice they look very different than either one of these two. There are no wings because wings are useless in space. You'll notice there is no rocket engine where the rockets can continuously run. In fact, you can't see any rocket engines at all. It's very misshapen because aerodynamics is meaningless in space. So once you get this vehicle in space, the shape doesn't matter and it does not need engines to continuously run. The Voyager spacecraft was able to visit 4 planets. And the way that this works is they put it on top of a rocket, they launched it into space, they pointed it in the direction of Jupiter, got it going very fast, turned off the engines, and then the spacecraft coasted all the way to Jupiter, because once you got it to the speed that you wanted it, it would continue at that speed until it encountered something. Jupiter's gravity changes the direction and slingshots it off to Saturn. Saturn's gravity slingshoots it and changes its direction off to Uranus and then off to Neptune. So what you can see is, in reality, when it comes to traveling through space, or traveling at all, Newton's first law is one that is actually governing what is happening. So an object in motion continues in motion in a straight line at a constant speed. Now in the next video, we're going to work our way towards Newton's second law. I hope you'll join me.